Yes. Some bookkeeping. This notation. Make sure you remember it. So, for example, if I put a polynomial, something like this, and take a to be x plus 3 and put a 2 here. And this, can somebody tell me what this equals to?
You're looking for the, you're not looking for V, right? If you're looking for a scalar, it doesn't work.
No, something. Yeah, that's what I want to say. Right? It's a subspace. Anyways, yeah, let me just look at it as a subspace. Yeah, so this would be 1 minus 2. Okay, so in general, if you have a matrix and we write A, again, it will be some numbers. Okay, so that's what this notation means. No, like a different, take some other basis for matrices. I said B, like a different guy. Yeah. Okay, so make sure you know this notation. Okay. Good. What? Who's a scalar? Which equation? This guy? Yeah, okay, so make sure you know this. So we have, so let's take the matrix 1, 0, 0, 0 and take the standard basis. What is that? So take epsilon to be the standard basis and put another one here. What is that?
So it's 1, 0, 0, 1.
Perfect.
Let's go like this.
Yeah.
All right.
Right. Yeah, today we can prove spectral theorem for normal operators. We proved it for self-adjoint. So make sure what self-adjoint means because it shows up. And but there are more normal operators than there are self-adjoint. So we proved spectral theorem for a small class of maps, but it turns out that it's true for a larger class. What are normal operators? These are the ones that commute with their adjoint T star. Okay, any questions? Oh, 1 minus density. Yeah, it's 1 minus 2. I should check that. Oh, man. I keep forgetting. So let's prove that normal operators are self-adjoint. So what happened here? Yeah, so T star, and you take its adjoint. So I'm doing another proof. Another proof is that adjoint of composition flips. Okay? And then this guy is equal to T star. And so what am I doing? Oh yeah, it's self-adjoint. So normal implies self-adjoint. Okay? Oh yeah. Sorry, other way. Yeah, self-adjoint as well. Thank you. So if you have self-adjoint, you get normal. What am I doing here? What am I proving? Oh no, okay, fine. I see what I proved. I proved that this guy is self-adjoint. Okay, good for me. Who cares? Okay, just a second. So, but the guy is self-adjoint. That means you can replace it by T star like this, and so you get this. So you get normal. Okay, so that proves the normality. No. T is equal to T star. I didn't take okay, again. T star. I need to get to T star T. T is equal to T star. T is equal to T star. I didn't do any switching. I just said T is T star. Because T is T star. Yeah, you put it, there's another T star up here. Yeah. And then use that T double star is T. Okay, everybody happy? All right. No, it is that simple. I made it complicated. But like the picture said, there are normal maps that are not self-adjoint, and so spectral theorem might not be true for them, but it is. So here's the example. Take the map that takes xy to y minus x. Okay? And if you like the matrix, it's this rotation matrix. So pictorially, you take xy, and what do you do? So this is y, this is x. You all right. So it's the rotation matrix by 90. And this guy is normal, but not self-adjoint. So let's find its adjoint. The way you find, well, you know what? We have I don't need to do this. So we know what T star is, the matrix T star. So can somebody tell me what's the relation between M T star and M? What's the matrix of the adjoint in terms of the matrix of T? Oh, wait. Yeah. What's the relation we proved? Huh? Anybody? Zoom people? How do I get the matrix of the adjoint from the matrix of T? We did it yesterday. Yeah. So T conjugate. So, but this guy is one was 0, 1 minus 1, 0. It's real, so there's no point for that, but you take transpose. So you get like this. Okay, so this is T star. You don't have to do the inner product. Okay, so if you can just use this relation, do it. Do not sit down with inner products. This is death. So what do I want to prove? I wanted to prove that it's not self-adjoint, and you can see it because this guy, which is T star, is not, this is M of T star, is not equal to the one of M. Okay, so not self-adjoint. All right? But they are normal. So they are normal because why? You have 0, 1, minus 1, 0 times itself times the T guy. Okay, so then you go like this, and then you do like this, and you do like this, and you do like this. So, and if you do the other way, you again get the identity matrix, okay? So you go like this, it becomes a 1, right? Why are you looking at me? Look at the matrix. Yeah, I checked both. Yeah, but it didn't have to be. I could have put other numbers here. Yeah, it's not always. Yeah. If what? Yeah, that's the definition of invertibility. Yeah, but that just happened to happen here. Don't try to get this. It's just an accident. Because what it says is that you go by 90 and then you go by minus 90. So you came back. That's all it happened. Nothing. All right. Right, so you're normal, but you're normal. So normal. Okay, so there are, if the rotation matrix, which is the simplest one in R2, is normal, you can imagine, but not self-adjoint, there's a whole family of them. So people became interested in these maps a long time ago, and they wanted a spectral theorem. So here's the spectral theorem. Going to prove it today. So we're going to show, like before, that if you're normal, if and only if you're diagonalizable. Okay, so if you commute with your adjoint, you can be written as a diagonal matrix. Okay. All right. Good. All right. So we have to build to it. Okay, so this is called isometry. Last week, we will do an application for linear algebra called SVD, singular value decomposition. Like people use it in data analysis. And one concept we need is called isometry. And again, I will come back to it, but this is just a prelude. So this is an isometry. It says that the adjoint operation is an isometry for normal operators. Okay? It preserves the norm. Whenever you see something like, whenever like, right, the rotation matrix. So R theta of V, if you take its dot product, okay, you get V back for all theta because you just rotate the vector. You didn't change the length, you just changed the angle. Okay, so R theta is an isometry. Okay. All right, so we'll come back to this. So yeah, so I have to prove you this, that instead of checking normality, you can just check isometry. Also, amazingly, the eigenvector of the adjoint is still the lambda bar. Okay, we talked about this last week. And what else? Oh, and they're orthogonal. So, what does orthogonal imply? Sure, yeah, and then what do you get from that? Yeah, there, but what else do you get from that? Why do they form a basis? Yes. So that implies Li. And so that's why we care about that. Because remember, proving linear independence was a huge pain. You had to like write down the thing, and you had to like check every coefficient, right, to make it 0, and you had to do some tricks. No tricks. Just compute the, just show that they're orthogonal. All right. I'm proving equal length. So this is the definition of normal, right? So they commute, so you can bring it to the left. Okay. Zoom people, questions? Then going from here to here, I think it's clear because 0 V, V being 0 is true because this is always true. 0 is orthogonal to everybody. But this other way is trickier, and I hope today I will explain it. So in general, whenever you have this statement for all V, you get that S is the 0 map. And this is only true over C. It's not true over real, because the example is you basically take TXY to be the orthogonal to it. So we want minus YX. So then TXY dotted with xy is equal to minus yx plus yx, which is 0. But this guy is not the zero map, it's the rotation map. It's not the zero map. It doesn't send it to the zero vector. This is not 0, 0. Okay, so this is because we're working with real numbers here. Whereas if you prove this for all complex, then indeed S of V is 0. No, here, you see this, so this statement here, it has to be true for all complex, not just for all. So this statement here that T V dot V 0 is only true for all real. Your assumption is weaker. So here your assumption with complex is stronger. You're asking it to be 0 in a larger space. Yeah. So asking it to be 0 for all complex. Here you're only asking it only for real. So you have more degrees of freedom that you're telling it, no, 0. We'll do the proof of it at the end. I just wanted to make sure to do the spectral first. Okay, then once you get this, then you just use linearity here. There's nothing. So, and this statement is exactly the one from the, I can ask you, yeah. So how do you finish from here? How do you show that the norms are equal? What? Compute what? Yeah, but how does this imply this? Okay, yes. Can you speak up? So yeah, okay, let me start from here. So it's TV equal to T star V, and then how do I go from here to here? Wait, just a second. What's the one thing I can do to get it? Yes. Lambda V. Well, let's not, we're just doing part 1 first. No, I'm asking, how do I go from, I hate this. This is garbage. I'm just asking, how do I go from here to the one he mentioned that I square both sides? How do I go from there to there? I just want to hear the word, one word that I want to hear. Yeah, that's all. It's just the adjoint property. Is that okay? So the guy here is equal to T star V, and the guy on the right is equal to TV, T star star V, and this guy is TV. Is that okay? Is that okay? Okay. So yeah, now let's do the other guy. So this is an eigenvector of T. So then by definition, this is 0. Okay. So this is the 0 element. So it's norm 0. And then you have that this equality from what we just proved. So So you have to check the following. You have to check that T minus lambda I, T minus lambda I star is equal to the other side. So namely, it's still normal, right? So we proved this part 2 for all normal maps. Now we have to show that T minus lambda I is still normal. Okay? If you prove that, you can apply part 2 to get this equality. And this, I hope you can see it from here, but it gives you the lambda bar. So let me prove this one first. So what's the left side? So this is T minus lambda I, and then adjoint is lambda star like this, and then this guy is T star minus lambda bar I star like this. All right, so now I'll calculus. And this, and this. Now I need to do. Let me check it. So okay, it's a mess. So T star, T this, this. T this, and then this. But this is equal to T star T. This is equal to lambda T star. This is T lambda bar. But then I star is I. And this guy is lambda squared. Then this guy is I star I, because we're using the I star is I. Okay? So you can check that this gives you the other side. So, okay. So you have normality, and so you can apply part 2. And so you have the isometry. And then, right, you bring in the adjoint. So again, T minus lambda I adjoint becomes T star minus lambda bar I. Okay, because I star is and I think you can say from here, right, that what did we prove? We proved that T star minus lambda bar I V is 0, okay, for all V in V, right? And what property of the inner product can I use to get my eigenvector relation? What is it called? I want to get T star V is lambda bar V. What should I say here? A small comment. Okay, it's called positive definite. I just want to make sure you remember the word, so you don't have to say No. I'm saying how to go from here to here. Yeah. Is that okay? Well, you just have to make the comment. Positive, definite. Just write this. You don't have to say anything else. People will know. Okay? Well, this was the axiom that x is zero if and only if x is the zero vector. So with itself is zero, therefore by positive definite, you're the zero vector. Yeah. Okay. All right. Just put, yeah. That's cool. All right. And what else do we prove? Oh, we have to prove that they're orthogonal, which is nice. You get a linear independence for free. So take two vectors of t. So remember, t is normal, right? So t star is t star t. And we're going to prove that u and v are orthogonal. So we just showed, though, that they are also eigenvectors of t star, but with a different eigenvalue, the conjugate. All right. So let's do it. So again, let me remind you, we want to show that uv is zero. That's what we want to show. Okay? All right. So we're going to compute this TUV in two different ways. First, you use eigenvector. So you get BU. Okay, so we're using the TU is BU. Okay, that's just the eigenvector relation, nothing fancy here. All right. Now we're going to compute this another way. I mean, I think you know this by now, right? This is just the adjoint operation. Okay, so I just take adjoint. And then I use what we just proved, namely that T star V is equal to the conjugate of the eigenvalue. Okay, and then from here to here, you use what, okay, I wrote it. So this is called conjugate linearity. All right, so remember, you have AV BU, and you get A B bar. Right, that's the kind of linearity you have for the inner product. So linearity in the first slot, conjugate linearity in the second. All right, just remember that. So I computed it in two different ways. So how to finish from here? Let me ask you. So how do we finish from here to show that VU is zero? Oh, no, that's fine. Yeah, go ahead. Right, so we just proved that this is equal to this, and then you have B minus A UV, and so equal to zero, and but B is not A. Yeah, perfect. No, because you have to tell them that why you have to write this at some point. Oh yeah, you could have done it here. You could have done like this, but say B is not A. Zoom people. Right. So good. That's it. We have all the machinery we need to prove spectral theorem, amazingly. So we're going to prove that T is normal if and only if is diagonalizable. So let me remind you that meant that there exists a basis B that is of V that is also an eigenbasis. eigenvectors. Okay? So, is that okay? So that's the one we're gonna use. It's much easier to work with. I think we're gonna use it. I don't know. Okay, we'll see. So for every linear map, we proved this week and last week that you can find a basis to make it upper triangular. Okay? Right? Remember, we proved this? Can somebody tell me what the diagonals were? Does anybody remember what they were? Wait, yep. The what? Yeah, they were just the eigenvalues of t. So it was AII was equal to lambda I. Yeah, we proved that Tuesday. All right. So we will show that this matrix is in fact diagonal because diagonalizable, like if your diagonals are the eigenvalues, then you have to be diagonal. If that makes any sense. If I give you a matrix representation of a diagonalizable map and diagonal are eigenvalues, then it has to be zero. That's what we're going to prove it down. No, how do you know that the rest of the entries are zero? You say diagonalizable says there is some basis. I have to prove you this basis is the one that gave you diagonalizable. So this week, I got you a basis to write you this. Now I'm going to show you that the same basis works to make it diagonal. Yeah. So we got this guy. We will show that it's also the one we want. All right. So we're going to use this isometry business. Right. So that's why I need this eigenvalue stuff. Okay, let's do it step by step. So if you stare at this matrix, the first column is the TE1, and the last one is TEN. Okay, and B is E1 to EN. All right. And if you look at this, you see that TE1 is just A11, or if you like, lambda 1 E1. Okay. So once you take their norms, they're the same number, but so there's no new information here. The new information comes when you look at the adjoint. So okay, let me remind you again, T star of B. So can somebody tell me what the matrix will be? Yeah, go ahead. Yeah, but what's the name we used? What was the name? I just want you to tell me the name. You said it like a few minutes ago. What? Yeah, that's all. Yeah. So you take conjugate transpose. Yeah, we're doing complex stuff. So we have lambda 1 bar, or if you like A11 bar, ANN bar, and then zero stuff, and then like this. Okay? Yes. Yeah, you're right. Thank you. Okay. Good. So, but this guy is just okay. So this is this is a result, but we have a definition of it. The definition is T star E1 all the way to T star En, right? This is definition. And this is a result we proved. And so that implies that if you look at the two matrices, you get this guy over here, that the first column is equal to this first column. And yeah, okay, let me do it. It's not, you don't have to see it. So we have that T star E1 is equal to 8 bar 1 1 E1 dotted with I mean summation A1N En, right? That's what equating these two matrices says. Okay, and then what do? You compute the norm. So T star E1, T star E1. So you have summation A1I EI and summation A1K EK. And I bring out the sums. I bring out, and then I have EI EK. And how do I finish from here to get the, what can I use here? Yes. Yeah, so the upper triangular, so there's a little bit of meat here. So we got a basis that gives you upper triangular. But by Gram-Schmidt, you can make it orthogonal. Okay? Yes. Yeah, no, I'm right. It's T star E1, T star E1. So you write T star E1 as a summation. The sum is over I1 and then K1, 2. It's a linear combination of the bases. So that's what the column means. It means that this guy is the coefficient of E1, this guy is the coefficient of En. And, right, so the only guy that survives is the diagonal stuff. So you get this guy squared and then times 1, because EI EK is equal to delta IK, which means, 1 when I is K and 0 when I is not K. So here's a new notation. Okay, you're free to use it in the house. So this bubble over here, in index notation, you can write it as like this. Yeah. Are you asking why I have I and K and not both instead of K for both? Yeah, so because let me see. Yeah. So right. So no, it's not from the matrix. This is calculus. So you have A1N En, and then E1 all the way to okay. I mean, you know what? We should talk about this at the end. I don't have time. So then once you do the crossing, you will get the thing. Yeah, you can just come. Okay. So if you do this orthogonality business, you get this this guy over here. Okay, because we killed off the orthogonal stuff. All right. So we showed this is T star. Right, and what am I doing here? Right, so what we just did, right. So in fact, I should go up here. So what did we just do? We showed that this guy is equal to TE1, okay? But this guy is equal to A11. Cancel out the A11. You're left with 0 is equal to A12 all the way to A1n squared, okay? This is a summation of positive numbers. So you get that they're all 0. Okay, so at least I want to finish this paper for now. So our matrix now will be of the form A11, a bunch of zeros, and then the first column is all zeros, first row. Okay, and then you still have stuff here. And so we just killed the first row. Is that okay? All right. And then you play the same game. So you look at the second column and you have the TE2 is equal now to 0 because we killed it. And then A22 squared and 0. Right? And then this guy is equal to T star A2, which is you take the transpose. I have it over here, I might as well go. So if you take the transpose, the second column in that matrix we had, so it was A11 conjugate, A22, A2n. Okay? And then stuff. But the basic point is that the second column will be the T star E2. Yes? Yeah, that's how you get this summation here. Remember, you told me how we use orthogonality. Yeah. Okay, and then let me do the punchline. So again, you equate the two, and you get that. Where am I? Yeah. So from here, you will get this would be A2. So the only guy that survives is the A22 guy, but then the A23 to A2n are all 0, same argument. Okay? All right, fine. So, yeah, I mean, that was the main point. So, I have a minute, so let me review what has happened. The hard work already happened Tuesday and Friday, where we found this orthonormal basis. And the point is, this isometry for normal maps allowed us to do a row echelon elimination. So it told me that, yes, you can start killing row by row of the arbitrary representation. Okay, so anyway, so thank you. Any questions, Zoom people? Yeah.
Sorry, this is a homework question. Is this supposed to be the evaluation at point t? Like p of t is like the evaluation of the polynomial. Oh, sorry. Have you seen the homework before? That you need to read?
Yeah, it's you evaluate the polynomial
At the point. Oh, okay.
Yeah, you have to
Can
use
you,
the
like,
representation.
Well, it's because like for D, you have to find the actual value. And I'm like, am I supposed to like differentiate both sides? Like, am I supposed to do calculus or is this like some linear algebra? Because it says find it for a specific T, and I'm kind of like you have to just like guess and check a bunch of stuff to like multiply by it and then get the evaluation.
Recall that this guy
Oh, sorry. Do you have time? I don't want to.
No,
like,
just a second. We can find a unique polynomial so that blah blah blah. You know, this what the polynomial have. While I'm guessing, you can find Q for this representation. Yeah. I mean, I don't think it would be a complete formula. That's what you're asking.
Yeah,
because
like
risk representation is an abstract result.
Yeah.
So, I mean, it's not, I don't think, will it be concrete? Will the cube be concrete? Shazwan, what's your question?
I was just wondering, so this is the process that we use to actually show that we can write the normal map as purely a diagonal matrix?
Yeah, have you seen that somewhere else as well?
No, I was just wondering like where this was getting to.
Yeah, exactly. So we proved the spectral theorem for normal maps. And I mean, it has to be up to change of basis. So you still have to put P inverse, right?
Oh, okay.
Where P are the eigenvectors of the map. But yeah, I mean, yeah, we have a diagonal representation.
Okay, that makes sense. Thank you.
Yep. Yeah, that's the thing. If you're there, yeah, right. So the rotation matrix, I think I'm gonna do it on Monday, has complex eigenvectors. Yeah, we saw it in the first week.
Okay,
So is it an abstract, this cube guy?
did you find a Q for question 3B? This is what's the polynomial? I'm assuming it's a polynomial of like X, right?
Oh, it's concrete?
But did you find an actual polynomial? Yeah. Oh, okay. Oh, okay.